Okay, hi guys. So we'll be continuing on seeing more on adiabatic process. So let's get started. So suppose in adiabatic we have already q equals to 0. So we can write that delta u would be equals to w. So for an ideal gas, we also know that delta h is equals to n cpm delta t and s delta u equals to w. So and we can also write delta u as n cvm dt. So from this we can write that the value of CVM as seen in the previous lecture was R upon gamma minus 1. So it would be R n into R divided by gamma minus 1 into dt. Okay. Rather it should be delta t, not dt, it should be delta t. So delta t can be written further as, or rather nr delta t can be written further as p2 v2 minus p1 v1 divided by gamma minus 1. This would be the value of delta u. Okay. So let me write some note here that this is valid for both reversible and irreversible processes. This is valid for both reversible and irreversible processes. Okay, now let's see the case for monoatomic gas. Okay, so for monoatomic gas we can write CVM is 3 by 2R. We have seen the how to derive the CVM value for monoatomic gas, diatomic and triatomic gas in our previous set of video lectures on physical chemistry. So just continuing from that, and CPM from the same can be written as, just add 1 R to it, so it would be 5 by 2 R. Okay, and gamma would be equals to CPM divided by CVM, that would be equals to 5 by 3. Okay, and now let us derive the value for polyatomic linear gas and non-linear gas when we are not considering vibrational degrees of freedom. So if vibrational degrees of freedom not considered, then we can write that A for polyatomic gas, or for polyatomic linear gas, we can write that CVM would be equals to 5 by 2R, and CPM would be equals to, just add 1 R value, so it would be 7 by 2R, and gamma in this case would be 7 by 5. Okay, so this is for polyatomic linear gas diatomic, which is diatomic in nature. Poly here is di. Okay, and for non-linear gas, the value of CVM would be 3R, value of CPM would be 4R, and value of gamma would be 4 by 3. Okay, next let us again rewrite the formula in case you are not able to recollect that. Let's say the formula is, if vibrational degrees of freedom are considered, so if vibrational degrees of freedom are considered, then we can write that, let's say n is the number of atoms in a molecule, then for diatomic gas n would be equals to 2, and for triatomic gas n would be equals to 3, and the formula is for polyatomic linear gas, we can write CVM value would be equals to 5R by 2 plus 3n minus 5R. Okay, and for polyatomic non-linear gas, we can write that CVM value would be equals to 3R plus 3n minus 6R. Okay, now this was just a summary for just recollecting back the values of CVM in various cases. Now let's see the reversible adiabatic ideal gas expansion and compression. So the next concept is reversible adiabatic ideal gas expansion compression. So we already know that du is equals to dq plus dw. So this is adiabatic, so dq value would be 0. So we can write that du would be equals to dw, which should be equals to minus p internal times dv. Okay, so and we also know that p external is equals to p internal plus minus dp. Okay, so we can write that NCVM dt is equals to minus this is du NCVM dt, and in place of minus p internal dv we can write that it would be equals to, now here p external would be nearly equal to p internal, as dp value is nearing to 0 or negligible, so we can write it would be p external times what would be v would be nothing but nRT upon again p or p external. So we can just cancel this out, or rather let's say we can just have the value of p internal here, which would be nothing but the value of p external, and the value of p external would be nRT upon v. So just putting the value of p internal as p external, as these two are almost equal, so we can put it that it would be minus nRT upon v times dv. Okay, so from here we can write that just cross multiplying the terms here on the left hand side, that is t going to the denominator of dt, and minus nRT upon CVM, or rather n and n get cancelled out, so it would be minus r upon CVM times dv upon v. So just integrating the terms here, so we will be getting integral of dt upon t, which would be equal to integral of r upon CVM dv upon v. So this can be written as ln t2 upon t1. So the limits are t1 to t2, and here v1 to v2. this should be equals to, now R upon CVM minus 1 would be minus gamma minus 1, and this would be again ln V2 upon V1. Okay, so just simplifying this, so we would be getting that ln T2 upon T1 would be equals to ln V2 upon V1 to the power minus gamma minus 1. So this would be nothing but ln T2 upon T1 is equals to ln V1 upon V2 to the power gamma minus 1. Okay, just adjusting the minus sign in the ratio. So we can write here that T2 upon T1 would be equals to V1 upon V2 to the power gamma minus 1, or we can write that T times V to the power gamma minus 1 is constant. Okay, so this is a very important result which we have gotten out of seeing the reversible adiabatic ideal gas expansion compression. So with this we come to the end of this lecture. In the next lecture we'll be seeing some more interesting things on the adiabatic process. So till then, good luck and goodbye.